All right, welcome to chapter 15, and we're going to look at buffers. And a buffer is any solution that resists changes in pH, and we'll get more into the function and how we build them in a little bit. And next week we're even going to build a buffer in lab. But let's start off with just the introduction. And a buffer is always produced from an acid and its conjugate base. And it doesn't necessarily have to be the same conjugate base, but for our purposes today, we'll use the same ones, because if we want to resist changes in pH, if we start to add a bunch of strong base, the acidic part will neutralize it. If we start to add a bunch of strong acid, the basic part will neutralize it. Well, how does this work? And the first thing that we're going to look at is something called the common ion effect. And let's take a look at this problem where we have something called acetic acid. And acetic acid has a formula that looks like this, HC2H3O2, and something called sodium acetate, and that looks like this, sodium, and then of course the acetate ion. That's the common ion. And what happens is the common ion tends to neutralize itself. Let's take a look. Let's say that I was going to ask you to calculate the pH of a 1 molar acetic acid solution. So we would say we've got a 1 molar acetic acid solution, and I was going to ask you to calculate the pH. And to find pH, you know that you need to get the H+. So the first thing that we're going to need is the Ka for this guy. So let's put up a table. It's got a bunch of Kas. Nope, couldn't do it. There it is. Okay, so here is all of our Kas. It says that acetic acid right here has a Ka of 1.8 times 10 to the negative fifth. So if I was going to ask you to calculate the Ka, we would say, if I was going to ask you to calculate the pH, you would do so by getting the H+. It's 1.8 times 10 to the negative fifth is the Ka, and the equilibrium expression for the dissociation of acetic acid would look like this, with H+ and the conjugate base on the top, and the undissociated acid on the bottom, like this. And we know that this is pretty small, so we're going to approximate. And so if we were going to try to find H+, it'd be the same as the acetate ion, and this is now 1. So what we have is 1.8 times 10 to the negative fifth equals x squared over 1, which is simply x squared. You get x of, let me take out my calculator. I know I had it, but I forgot. 1.8 times 10 to the negative fifth. We're going to take the square root of that. 1.8 times 10 to the negative fifth. And you get 0.004 something, 0.0042. This is equal to H+. And if you plug that into our equation for pH, where we say that pH is equal to the negative log of our H+. Let me bust out my calculator so you can see what I'm doing. And so we would say negative log of our H+, 0.042, and you get a pH of 2.38, we'll call it. Well, what happens if you build a buffer? It's supposed to resist changes in pH. And that means it's got some conjugate base going on in there. What happens? What happens is that this thing called the common ion effect reduces the influence of any ion that's already in there. Let's go back a couple weeks and let's do something called an ice table. And we remember this from chapter 13. And so we're talking 1 molar solutions of acetic acid, H2H O2, and 1 molar sodium acetate, and that looks like this. All right, so what we know is that if we were going to try to calculate the pH of something like this, let me move this over a little bit so I have some more room. If we were going to calculate the pH, we would want H+, and that means dissociation. So what's our initial concentration of H? C2H3O2? 1. What's our initial concentration of H+? 0. What's our initial concentration of C2H3O2 when we start this off? Now, if this was just a regular acid, this would also be 0 because we would wait to see what the dissociation was. But we already have some here, and this is going to dissociate completely. That means that when this gets put into solution, our concentration of the acetate ion is already 1. So what's the change going to be? Well, we've got to run it forward because we've got to make some H+. So this is going to decrease by X, and this is going to increase by X, and this is also going to increase by X. So at the end, this will be 1 minus X, and this will be plus X, and this will be 1 plus X. But, I mean, this Ka is really small. So we're already going to approximate. That means that's just going to be 1, and that's just going to be 1. So what happens when we calculate the pH? Let's plug everything in. Ka equals 1.8 times 10 to the negative fifth. That's equal to H+, and C2H3O2. Now, when we did it in the previous example, we didn't know either one of these, and they were both X. In fact, they increased by the same amount, so they were the same. We also have H, C2H3O2 on the bottom. Well, we don't know H+, right? Because that's still going to be X. But everything else is 1 in this case. And of course, those guys cancel out. Now, they won't always. You might actually have to solve for X. But this guy right here, this being X, that's easy enough to solve. X equals 1.8 times 10 to the negative fifth. Even if these were different, you could just solve for X like we normally do. So what's the pH? Now, we said that a buffer is supposed to resist changes in pH. And previously, this concentration of acetic acid had a pH of around 2.37 or something like that. Fairly strong, fairly acidic pH. What happens when you build a buffer where there is some common ion effect? 4.74, meaning pH is way higher, meaning it's way closer to neutral with some common ion effect. And that's all I'm going to ask you guys to do for today, is being able to calculate the common ion effect of a buffer which has 2 common ions. Or even if they're not common, one will act as an acid and one will act as a base. And their concentrations may be different. For example, if this was 0.6, you could still solve for X by, solving for X. You guys know how to do that. So let's take this for a spin. I'm going to ask you to try a couple of these and be on the lookout for common ions in solution. All right? I'll talk to you guys on the next one.